Have you ever wanted to build your own programmable LED panel? Well, today I'll show you exactly how I designed and built a 91 LED RGB LED matrix from scratch, including schematic design, PCB layout, and programming custom animations with the Arduino NeoPixel library. I'll share some common mistakes to avoid and how to get your PCB manufactured quickly with today's sponsor, PCBWay. This project is great for LED displays, signs, or just making cool lighting effects. So let's jump right in, starting with the schematic. At the core of this design is the XL-5050RGBC, which uses WS2812 driver internally, which is a very common driver for these types of LEDs. And basically the driver is an inbuilt controller for the RGB LEDs that are present in the component. It works with a single wire data protocol, which means we can daisy chain multiple LEDs together and control them with just one pin from a microcontroller like an ESP32. For my microcontroller, I'm going to be using one of my other boards because I did not include any microcontrollers on this panel, as there would have been too many components for me to order. Now each LED can draw up to 60 milliamps when fully lit, meaning that at full brightness our 91 LEDs could pull over 2 amps. Now to handle this, I designed a PCB with thick power traces and added bypass capacitors near the LEDs to stabilize the voltage for the logic drivers. This is also recommended by the datasheet of the component. So you can see I've got my LEDs arranged in a grid on the schematic over here, and all the LEDs I've got on top. Now the voltage coming from my ESP32 is going to be a 3.3 voltage logic. For this, the LEDs themselves, they need a 5 volt logic, so I needed to include a level translator. So you can see this component over here, which basically takes in the 3v3 voltage over here and translates that to a 5 volt logic level over here. For the power input, I went with the USB-C connector, which provides 5 volts and enough current to power all the LEDs safely. Now I've not added any protection or anything like this on this board, just because I'm not making this for production. But if I was to make this board for a production, I would probably add in some TVS diodes and some fuses maybe, just to make sure that everything runs smoothly and reliably. As you can see with my daisy chaining, the LED, first one over here, is connected to the next one. So the data out of the first LED connects to the data in of the second LED, and so on. When it gets to the end of the row, this LED connects to this one over here. Now I think if I was to relay this out after doing some testing already on this panel, I would probably connect them in this direction, which would give me slightly better display algorithm, but I have managed to get this orientation or this connection diagram working properly. The schematic itself is very simple. The only thing additional to the LEDs and the capacitors and the level translator over here is the USB-C connector, and I've only included 5K1 resistors on the CC line. I'm not doing anything with the data line, so I've left them unconnected for now. So again, a very simple PCB for this panel. Alright, now that we've looked at the schematic, let's move on to the PCB layout. As you can see, I've just made a rectangular panel with these LEDs with 13 LEDs or 13 columns of LEDs and 7 rows. I'll be using all 7 rows to display text, and then obviously we can do all kinds of patterns with these LEDs because they are RGB. One of the things you have to be careful with, the LEDs are going to require a lot of current. So I've tried to basically use a solid connection for my 5 volts and for my ground. So you can see the 5 volts is on the top layer over here, which is the 5 volts going to the LED. And then the ground is basically on the bottom layer, and it's a solid ground. Obviously the most important thing, I've got my engineering experience logo over here. I think something like this, you want to keep the spacing between the LEDs consistent. What I should have done from just when I show you the panel, you'll see, is close up the space a little bit, which will make the text look a little bit nicer. But that's something I can keep in mind for next time. Now, I already mentioned that I should have basically connected the LEDs in this direction and basically gone like this as a zigzag. Whereas right now I've gone like from here to here and to here. And you can see the tracks coming back all the way. Now the layout would be slightly better in terms of data integrity and stuff like that if I basically went in this direction. So for my next board, when I do revise this, I will make sure to go like this. Now, as far as I know, this hasn't caused any issues with functionality, as the board does work properly. But rearranging it in this format will mean that the data lines are shorter and not unnecessarily long. When you're designing something like this, and before you send it off to manufacturer, you want to make sure that you do a DRC check and an ERC check. So I'll just quickly show you how you can do a DRC check on something like this. You basically can click this button, click run DRC. Now all my errors are basically saying that my library doesn't match, and this is because I've recently upgraded to KiCad 9 and the PCB was designed on KiCad 8. So we can ignore that. We can see I've got no unconnected nets and no other errors on this board at all. So when I did do my original DRC check, I had 0 errors and 0 warnings, and it's all fine in terms of just checking any design rule violations. Some of the design rules are based on your own requirements. So such as this board, you'd have a design requirement for track thicknesses. So if you're running 2 amps on this board, you'll need to have a track that's at least 0.78 to keep the temperature rise under 10 degrees C. So that could be one of your design requirements. Some of the other design requirements stem from your PCB manufacturer. So for example, PCBWay, they have a page on their website that shows their capabilities. So you don't want to make tracks too thin, or you don't want to put components too close to the edge to make sure that you're not violating any of the rules. Some things like track thicknesses can increase the cost as well. So for example, if you were to place a 0.1mm track on this board, it would be more costly than placing a 0.15mm track. So those are the kind of things that you want to keep in mind. So with a successful design check and a DRC check, I was ready to order this PCB. You can see all the LEDs are nicely laid out. I've got a USB-C power socket over here, and I've got a data input which is coming from a microcontroller on my ESP32 board, but you can connect an Arduino to this if you need to as well. Arduino's already run at 5 volts, I think, so you may not need the level shifter, but this is the part that's doing the level shifting. So it's taking in 3v3 and then it's basically turning that into a 5 volt signal for the LEDs. Now in terms of the capacitors, I've basically added 100 nano capacitor per 2 LEDs. Now the datasheet for the LED itself recommends you have 1 capacitor per LED, but this seems to work fine, so I will try and reduce them further, because I don't want to have unnecessary components on the board. Obviously, reducing the components or reducing the capacitors may mean that the board fails to work under certain circumstances. For example, if the power supply is not as smooth as the one I'm giving the board right now. So there's things you have to be careful with when cost cutting like that. But yeah, I think I'll be safe with removing the boards. Another thing I can do is potentially add in a large capacitor somewhere around here, like a 5 microfarad or something like that, just to provide some capacitive decoupling from the power lines and the cables that are coming in. Now that my PCB is ready, I'm going to get it made, and for this I'm using PCBWay. PCBWay is an awesome place to get high quality PCBs manufactured at an affordable price. So you just upload your Gerber files to the website, select your specification for the sensor. You can see there are a lot of customization options already. You can choose different PCB colors, different thicknesses. You can also get flexible PCBs as well, different material finishes. You specify if you want an assembly service and whether that assembly service is going to be turnkey or you're going to provide the components, and you save the cart. Your uploads will get quoted and you can place the order. One thing I love about PCBWay is their fast turnaround time and the quality of the manufacturing. I've also found that their staff is very helpful if you have any questions that you need answering. So if you want to get your own PCBs made, check out the link in the description and you can get yourself a nice little discount. And once again, big thanks to PCBWay for sponsoring this project and making this PCB and this tutorial possible. For development and testing, I'm using the Arduino IDE to write some code using existing libraries. So I've played around with 2 different libraries that can be used with my LEDs that I've got on this board. The first one was fastleds.h, and then the second one, which I'm using at the moment, is called the Adafruit NeoPixel.h, and both of these libraries were quite good in terms of getting the board running very quickly. So you can see I've written a bunch of code on the screen now that kind of sets my font. So basically I've got capital A, B, A to Z, I've got letters, I've got numbers 0 to 9, I've got some regularly used characters, and that's all I've set up for now. Obviously you might need to set up more of this. Basically I did it using Excel. I'm sure there's existing data libraries for this kind of thing on the internet. This byte of data over here is for the first column, and then this is for the second column, third column, fourth column, and the fifth column. Now the individual bits in here, so obviously you've got 8 bits, correspond to LEDs, except for the last bit, which obviously I've only got 7 LEDs on the board, so the last bit is always 0. So I did that all on Excel, basically just created my characters and then exported out my characters onto this table. I think R is still a little bit wrong, which I need to fix, but that doesn't really matter. I don't think I'll be using this that often anyway. And I think if I was doing this for real, I'd probably use an existing library. There's probably one available on the internet anyway. The code itself is very simple. As I said, we're just using this library. We've defined our pin, which is going to be the data output pin on my ESP32 board. I've got 91 LEDs on the board itself, and they are laid out 13 by 7. I'm just starting the strip, which is all part of the NeoPixel code, and then I'm going through a bunch of cycles, which does kind of the rainbow, which you've seen, then a message. If you want it to scroll in from the right to left, then you might want to add in some spaces, otherwise the code at the moment starts from the first LED and you sort of miss the H when it starts to scroll. Then basically you can do a bunch of different effects, and a lot of it is fairly easy to set up. So the way this code works, or way these LEDs work, is with a single wire data line, which basically, if you the single LED expects 24 bits of code, but I don't know what it's saying down there. I'm using a Chinese manufacturer for this to keep the cost down. We're going to have a look at this data anyway on a picoscope to fully understand what's going on with the code, as I'm currently just using the library. Obviously, you want to know what's going on inside the library so that you can debug any problems that you may face. So what's going on? You send 24 bits, let's assume 24 bits for now. Then you have a reset timing where you don't send anything. So what you do is you send 24 bits of information. In those 24 bits, the first or the last, I'm not sure which way around this is for the blue. The second or the middle 8 bits is for the red, and the last 8 bits is for the green. And I think if you basically change the value of the green, that changes the intensity. So if all of these were 255, 255 and 255, then you've basically got your full brightness white. Or if you want your full brightness green, then you send all of these as ones and the rest as zeros. So pretty straightforward really. If you have 91 LEDs, you basically send 91 times 24 bits without any gap. If you have a gap of more than 80 seconds in the transmission, then the first LED will count that as a data for itself. So it will stop transmitting the data onto the next chip. So these chips, as we saw before, are connected in series. And what happens is when you send, let's say in this case it's 3 LEDs, if you send data to 3 LEDs, the first bit of data that was sent will get transformed or will get transferred to D3. And we will have a look at this, how the LEDs transfer the data in a bit more detail very soon. Basically I will adjust the code so that we'll send some distinctive code for LED 1 and LED 2 to see how the transmission works using a picoscope. But what happens is that the data that the first LED doesn't need gets transferred to the next LED onwards. Now I'm not sure if it sends the first or the last byte. I assume it would be the last byte and it keeps the first byte, but I might be wrong on that. I mean, it could potentially send the first 24 bits onwards until it gets this stop time over here. You've seen the simple code I have. I think the trickiest part of this code was basically trying to map the letters to the indexes and get that working properly. So getting this character index and basically configuring the code in here so that it works with the way I've arranged the LED panel, which at the moment goes this way. So goes from D1 to D13, and then D13 is connecting to D14. I should have connected to D26, or maybe I should have gone this way, which would have been a little bit better in terms of the coding complexity. But it's not too bad once you kind of figure out which way the data is flowing. I will be uploading all this code to GitHub, so you can basically download this and play around with it as well. And I will be uploading my project to PCB Way, So if you want to download the project yourself, or if you want to order the project from PCBWay for yourself, then you can do that as well. There are a bunch of LED panels available that you can buy off the shelf, so maybe you want to do that to play around with these LEDs. I like designing my own stuff, so that's why I did it like this. So let's now modify this simple code so that we are basically just sending data to 2 LEDs instead of 91 LEDs. So I'm just going to program this up with the rainbow cycle. I need to make sure I turn my board on. So on the screen now, you've got basically data that's going into the LEDs. I'm running 2 channels at the moment. The first channel is the data coming out of the ESP32 and data that's going into my logic level translator. So you can see it's 3v3. If I bring this bar down here, or roughly 3.25 volts. And the second line is the data going into the second LED, which has been kind of translated to 5-volt level. Basically, I've configured this to have 2 LEDs only. The first byte that's sent out from the microprocessor gets sent forward to the second LED. So you can see this extra, or these longer pulse widths are basically at the input of the second LED, and the longer pulse width represents a 1, which is approximately 800 nanoseconds in this case, as you can see over here. And the shorter pulse widths, which if we have a look at one of these, is anything less than 400 nanoseconds. So it doesn't actually turn to a logic low, as in a logic 0 or anything like that. It basically changes the width of the pulse to get a 0 and a 1. But it's not a continuous pulse width, so it's not analog pulse width. It's just a difference between, let's say, approximately 400 nanoseconds and approximately 600, 700 nanoseconds to represent a 0 or 1 respectively. So you can see from here, the first byte of data that was sent out starts from here. And as time goes on, basically we start getting our second byte, which starts from this end over here. The red signal is what's going on to the second LED, which comes in later on and is transmitted last by the microcontroller. So the first chunk of 24 bits is kept by the first LED, and then the rest is transferred forward. So obviously if we were using 91 LEDs, then there will be a lot more data on this side, which will be transferred forward by the LEDs that follow it. So quite cool how these things work, and a very simple protocol to control the light levels. You can see the first 8 bits, so that's 1, 2, 3, 4, 5, 6, 7, and 8. Is basically for the green color. First 8 bits is basically for the green color. The second 8 bits is for the red. So 1, 2, 3, 4, 5, 6, 7, 8. Obviously in this sketch or in the code that I'm doing now, I've turned off red completely to understand the data stream a little bit better. And then the last 8 bits is the blue, which you can see over here. So to reiterate, for the second LED, the green is off, the red is off, and the blue is on. And for the first LED, the green is on, the red is off, and the blue is also off. So we're getting a green and a blue shown on here. So now you've seen some cool patterns on RGB LEDs and how the data stream works as well. You can change the patterns to anything you like, but the more LEDs you add, the larger the delays will be. So if you were to kind of have a faster animation, or if you needed something faster in terms of things you're trying to display, what I would say is you have individual data lines going to rows of LEDs, then that will make it a little bit faster in terms of what you can display. But then if you're looking for patterns like that, then you might want to go for a display anyway. So quite cool for simple graphic displays, whether you're trying to show temperature or anything else, you might just use a single LED. A full LED can show you a clock as well, so that's quite good. Obviously for a clock, I think you might want a few more LEDs, I'm not sure, because the number of LEDs I have at the moment, obviously you saw the number of characters I have. I think I can get 3 characters on there with the kind of size of characters that I did. Maybe you can do a better pattern in terms of the arrangement for how you display the characters to get more on the screen, but it wouldn't look very good. And I think we would probably want to reduce the gap between the LEDs as well to get a slightly crisper display, slightly better looking display in terms of this gap over here, which we can close up quite significantly really. So yeah, we have a working ARGB LED panel. Quite pleased with what we've got here, and I think I've learned how these RGB panels work as well in terms of the data stream. I'm sure other LEDs such as these work in slightly different ways, so make sure you read the data sheets before putting them on a PCB. So there you have it. We went from a schematic PCB design, ordered with PCBWay, did our first build and did some coding and did some testing with a oscilloscope. Hopefully you found the video useful. Let me know in the comments if you would like me to cover other things on the ARG panel or other schematics or other projects that you would like to see on this channel. What I would love to do is maybe control the ARG panel using Bluetooth or something like that. Then maybe we can use it as a light going forward. If you want these boards for yourself, drop me a message and I can ship them out to you as well. Again, a big thanks to PCBWay for sponsoring this video and making this project possible. Don't forget to like, subscribe and turn on notifications for other projects. I do have some more Art of Electronics videos coming out soon as well. And then I have plenty of other projects planned for this year. So really looking forward to that. Thank you for watching. Bye for now.